Hello, I'm Rajesh Bhaskaran. I have a fun job teaching engineering simulations at Cornell University. I help prepare our students to use simulation apps that are very important in engineering analysis and design. In this video, I'm going to demonstrate how Amazon Appstream 2.0 allows our students to use any computer to run graphics-intensive simulation applications like ANSYS Fluent in a web browser. And the particular simulation I'm going to show you is airflow over a wind turbine rotor. My vision is the democratization of simulation, and Appstream enables that by putting simulation apps at students' fingertips. At Cornell, we have been piloting Appstream in select courses to enable students to access course software from any device at any time. For one of the courses, previously we have distributed course software on CDs through the Cornell bookstore. Now, with Appstream, students are able to access the same software in a web browser, irrespective of the kind of personal device they have. As you can imagine, this is logistically much simpler. It has also enabled us to bring hands-on software instruction into discussion sections because students are able to access the software from any device. Most engineering design and simulation applications are PC-based, while many of our students have Macs. And Appstream now enables students with Macs also to run these PC-based applications. Students don't have to worry about getting a particular kind of laptop or messing with application configuration or finding a free computer lab. They just open up a web browser and get the same consistent experience as if the software was installed locally. Appstream makes things simpler for me. It's usually a problem finding a suitable computer lab during popular course times, and I have to tear my hair out in doing that, and you can see the effect of that. That worry goes away with Appstream. It also makes life easier for our IT department. Appstream is fully managed. It's secured within a web browser and has access to our existing network. So the IT folks don't have to worry about application distribution, which version is installed in which computer lab, or about securing these applications. These are just some of the ways in which Appstream enables exciting new ways of teaching and learning while also making the technology environment simpler. Let me move on to give you a demonstration of the wind turbine blade simulation taken from our wind energy course. Here is a model wind turbine rotor that is designed and 3D printed by students in our wind energy course. This 3D printed model didn't come out quite right, so it's become my prop. Students test these models in the wind tunnel to predict what kind of power they can extract from the wind with this kind of design. Another group of students does a simulation to also predict what kind of power they can get from this design. Let me show you the simulation running in the Appstream. So this is Appstream is running in a tab of the Chrome browser, and when students come in, they can pick between different applications. The particular application I've picked is ANSYS, which is an industry standard for these kinds of simulations. This shows you the blade in ANSYS. So this is the same geometry that students test in the wind tunnel, and using some mathematical tricks, you simulate flow over a single blade rather than three. And if I zoom out, I can see there's a region around the blade, and you're simulating the flow between the blade and this outer region. And you have to divide this region into little chunks for the solver to approximate the equations on those little chunks. That's called meshing. And this is an outer view of the mesh. And let's take a look at what the mesh looks like as I cut through it. So if I cut through the mesh and I zoom in, okay, I can see, I have much finer resolution near the blade. That's where most of the action is happening. So you need finer resolution. So you need to interrogate what's happening with the mesh near the blade. And then you can actually move the cut plane or the section plane. And this is really important to interrogate what's happening with the mesh near the blade. And I can't tell when I do this that I'm running on a remote machine, and that's really very impressive. And then you get the solver to solve the equations, and then you can look at the results, which is the most exciting part. So this is single blade reflected twice to show you 3 blades, and we ignore the hub. These are pretty challenging simulations, and so we try to make as many approximations as we can, you know, as at least when we start off, and then we can bring in the hub at the next level of approximation. I can look at the pressure over the blade. So let me take a look at that. Red is higher pressure. So where the wind is coming and hitting the blade, you have higher pressure. And behind, you have lower pressure, which is indicated by these blues and greens. But really, one has to interrogate whether these values of pressure make sense. And that's the kind of engineering judgment we try to teach. And you can also look at what the flow is doing over the blade. Let me show you that. So I'll go to a single blade and then enable what are called streamlines to see what the flow is doing over the blade. And the idea is that, let me manipulate the view here, is that when you release a fluid particle over here, it's going to follow this trajectory. And you see that there is, you know, a dead water region over here that leads to losses, and this blade needs to be redesigned to minimize that. So that's a quick demo of a cool simulation run in a web browser using Amazon Appstream.